The Thames is a tidal river. That single fact means London has always been one bad storm away from catastrophe. The city sits on a floodplain, and twice a day, the sea pushes back against the current. For most of history, Londoners lived with that risk and occasionally drowned in it. The barrier that now stands roughly 2 miles east of the Isle of Dogs stretches more than half a kilometre across the river. Its 10 steel gates, when raised, each stand as tall as a 5-story building. The structure has been operational since 1982, and it guards more of Greater London's floodplain than any previous flood control measure in British history. But getting to that solution required confronting a problem that for decades engineers could not agree how to solve. The core contradiction is this: you cannot simply wall off a tidal river. The Thames needs to breathe. Ships have to pass. The river has to drain. Any permanent barrier would strangle the port, flood the riverbed at low tide, and turn the upper estuary into a stagnant pool. Yet without some kind of barrier, a sufficiently powerful North Sea surge could push a wall of water upstream and swallow large portions of the city before residents had time to evacuate. That is the problem the Thames Barrier was built to solve. Not how to stop the sea permanently, but how to close off the river exactly when needed and open it again when the danger passes. The threat from the North Sea is not theoretical. Storm surges form when powerful low-pressure systems drag water across the shallow shelf of the North Sea and funnel it into the narrowing channel between Britain and continental Europe. As the funnel tightens, the water piles up. The Thames estuary acts like a natural amplifier, concentrating that surge as it travels inland. The further upstream the surge reaches, the higher it climbs above normal tide levels. London, positioned at a point where the river bends and narrows, is especially exposed. The response to that risk had to be mechanical rather than static. A fixed dam would block the river entirely. A levee system along the banks would protect individual neighborhoods but leave the water nowhere to go. Engineers needed something that could be deployed on short notice, hold against thousands of tons of surge pressure, and then retract completely to let the river function normally. The solution they arrived at is deceptively elegant. The Thames Barrier uses rotating sector gates. Each gate is a curved steel shell, roughly the shape of a quarter cylinder, that rests in a concrete sill on the riverbed when not in use. In that position, ships pass overhead as they would on any other stretch of river. When a surge is forecast, hydraulic machinery rotates each gate upward through 90 degrees. The curved face rises from the riverbed, pivots through the water column, and locks into a vertical position that faces the incoming tide. The gate does not slide or swing like a door. It rolls, using the geometry of its own curve to move through the water with far less resistance than a flat panel would require. That rotational mechanism is the engineering decision that made the barrier possible. A flat gate of the same height and width, raised vertically from the riverbed, would require machinery powerful enough to lift its entire weight against the pressure of the water above it. A rotating sector gate shifts that load. As it rises, the curved surface redirects hydraulic pressure rather than fighting it directly. The gate becomes easier to move the further it rotates, because the geometry continuously changes the angle at which water acts against it. The visible piers between the gates house the hydraulic machinery that drives each rotation. Those distinctive silver-clad structures, curved like inverted boat hulls, are not decorative. Their shape sheds wind load. Their interiors contain the operating equipment, and their foundations anchor the entire gate assembly against the force of a surge pressing on the closed barrier. Each pier sits on a concrete base driven into the riverbed, and the riverbed itself required significant engineering work before construction could begin. The Thames carries heavy sediment loads, and the geology beneath the river is not uniform. Building stable foundations in a tidal river while keeping the river navigable meant working in stages, diverting traffic, and managing cofferdam construction across multiple years. The barrier spans the river through 4 main navigable spans and 6 smaller ones. The 4 large gates protect the principal shipping channel and bear the greatest hydraulic load during a closure. The smaller gates on either side handle lower energy flow, but are equally necessary to seal the full width of the river. Closure is not instantaneous. When a surge warning is issued, operators raise the gates progressively, coordinating the sequence to manage water levels on both sides of the barrier and prevent trapped water from backing up dangerously into the upper Thames. At low tide, the barrier can be opened again, releasing the impounded water seaward and restoring normal flow. That tidal cycling is built into the operational procedure because leaving the upper river sealed for extended periods would damage the estuary ecology and affect drainage from tributaries upstream. The barrier's northern bank sits in Silvertown, in the London Borough of Newham. Its southern bank is in New Charlton, in the Royal Borough of Greenwich. Both banks required extensive approach works, concrete walls and embankments that tie the barrier into the broader flood defence network protecting Greater London's floodplain. The barrier alone does not protect the city. It is the anchor of a system that includes the raised riverbanks downstream and the flood walls further upstream. A surge that the barrier stops at the estuary would otherwise simply spill over those walls. The whole network depends on the barrier closing in time. The Thames Barrier became operational in 1982. In the decades since, it has been closed hundreds of times to protect against surge events that would otherwise have caused flooding across significant portions of Greater London. The frequency of closures has increased over time, a pattern consistent with rising sea levels and changes in North Sea storm behaviour. Engineers and planners have publicly noted that the barrier was designed with a specific range of tide and surge levels in mind, and that continued sea level rise will eventually push conditions beyond what the current structure was built to handle. That uncertainty is genuine and unresolved. The barrier is not a permanent answer. It is an engineered response to conditions that are continuing to change. What it demonstrates, concretely, is that a retractable closure can protect a major tidal city without permanently severing the river from the sea. The river-hulled tidal surge barrier, the second largest flood barrier in the United Kingdom, operates on a related principle. It holds horizontal when not needed and rotates downward to the riverbed during a surge, similarly preserving normal river function between events. The Thames Barrier did not solve the problem of London and the sea. It bought time, and it proved the mechanism. A rotating gate, seated in the riverbed, invisible to river traffic until the moment it is needed, then rising in a controlled sequence to hold back a North Sea surge, is a workable answer to a constraint that once seemed to have no answer at all. The constraint was always the same. You cannot close what must stay open. The barrier closes it anyway and opens it again before anyone has to notice. The deeper question, the one the barrier's engineers knew even as they designed it, is what happens when the surges grow larger than the gates were built to resist. That question has no current answer. It has only a current deadline, and the deadline is moving. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.